So hi, I'm Sebastian. I've been doing things with PHP and to PHP for a really long time now. I don't know how long exactly. I only know that like 18 years ago, I started to work on PHP unit and gave my first presentation at a conference. And for about 1 or 2 years before that, I was already using and doing things with PHP. And when I'm not at a conference or working on open source, I help customers, teams build better software using the PHP ecosystem, everything related to knowledge transfer, consulting, coaching, training. I do that with my company, the PHP Consulting Company, together with Arne and Stefan, who are also at this conference. That's all the sales pitch you're going to get out of me. Which brings me to this rather awkward slide where I share some secrets with you. Secret number 1, there are many things that I at least think I'm good at. Dancing and singing are not one of those things, so please don't be disappointed if I don't sing and dance during the next 45 minutes. That's in all our best interest. Why am I saying this? After my presentation this morning, there was some disappointment voiced on Twitter that I did neither do dancing nor singing on stage. Sorry. Second secret, when you present at a conference like this one, you have to figure out what you want to talk about, like, depending on the conference, 6 to 9 months ahead of time. And that's usually, so now it's June, so right before Christmas preparations, hectic time of year, I had to figure out what I wanted to talk about here at this conference this week. And I had already the idea for the talk that I gave this morning, but I needed another idea. So I asked around, and somebody suggested, hey, there is this new thing that everybody talks about, like 9 months ago, everybody was talking about self-contained systems and that you need to build them and everything will be awesome. So Sebastian, at IPC in Berlin in June, you'll talk about testing self-contained system. I said, okay, that sounds like an interesting idea. I wrote an abstract, and that abstract got accepted. That's why I'm here today. Along the way, I figured out that, well, I'll leave that to the end. So that took me on a really interesting journey. At least I thought it was interesting, and that's the journey that I'm going to share with you today. It involves looking a little bit into the past, how the architecture of the applications that we develop has evolved over time. So with the secrets out of the way, we can start. Or, yeah, we'll talk a little bit about testing. We talk about self-contained systems, yes. But what I'm not going to talk about is like things like this. I'm not going to talk about hype-driven development. Yeah, that's what you usually get, or what some people get out or take away from a conference presentation like this one. I have heard a new buzzword. And Monday morning when I'm back at work, I need to do self-contained systems. I don't know if I need them. I have not really understood what they are. I mean, in 45 minutes, how well can you really understand a new topic? But it's cool, it's new, I have to have it. Please don't do that. I just want to give you an idea that you know what you're talking about or what others are talking about when you hear that term in the conversation. I'm not going to tell you you have to do any of this stuff that I'm going to talk about right now on Monday morning, whatever. So no hype-driven development. Also, no Reddit-driven development, which is I read something on Reddit and 1,000 people said, this is really cool, we need to do this. No. Conference-driven development is actually not that bad. That's how open source, or that's how work in open source projects gets done, either because somebody who's working on the PHP core or on a component in the PHP ecosystem needs a new topic for a presentation, so he or she implements a new feature for PHP itself, for a tool like PHP Unit, or a completely new tool. So that's conference-driven development. The conference, the deadline of the conference keeps you motivated to implement something new in your spare time in the open source project. Again, that's not what we're talking about, also not Stack Overflow-driven development. That's what I see in some parts of the world really frequently, that people, even though I'm on site and coaching developers to learn a new tool like PHP Unit, for instance, instead of asking me while I'm in the room, they go on Stack Overflow, search for something, do copy-paste into their IDE. And there are even plugins for IDEs that do this automatically for you. Don't do that. This is a rather new trend, packages-driven development. Packages is awesome, Composer is awesome. The problem is, it's so awesome that it's too easy to integrate new dependencies into your project. So you have a problem, you go on packages.org, you search for the problem, you find a package, Composer require vendor/package, and you have a new dependency in your system that you have not evaluated, that you do not know whether it's still maintained or not. Don't blindly add dependencies to your project like that. Yeah, so I promised a look back into the past. And we go as far back into the past as late 1960s. Last time I used those slides, there was at least one person in the room who didn't know the movie. Do we have someone here who does not know which movie this is from? 1, 2, 3. Okay. 2001, Space Odyssey, the monolith. So 1968, how did we build software systems in 1968? Well, I didn't build software systems back in 1968. That was 10 years before I was born. But what was built back then was, the state of the art was building monolith. I mean, back in those days, you were lucky if you had a computer that fit into one room. Usually, computer filled multiple rooms, so it was only natural to have applications that were built as one big thing, and if you wanted to change some little thing, you had to change everything, because everything was interconnected with each other. And basically, you talk about a monolithic system when there are no indistinguishable parts in there. Everything is related to everything, and you cannot point at one specific area of the code or of the application, say, this is the point in the application where we deal with checking our business rules. This is where we talk to the database. Everything does everything. That's not really what we want. We didn't know really any better back then. I'm really happy that I was born 10 years later, but it took a while until things got really better. So that's the kind of monolith that keeps you up at night, that does not let you go to sleep, that gives you nightmares. And I've seen that a lot. I've had lots of experience with teams that have a monolith like that, soft piece of software that is 5, 10, 15, 20 years old. And yes, there are applications written in PHP that are over 20 years old and that are still used today. They started with PHP FI and are now running on PHP 7, which is amazing. But still, it's usually one big blob of code, a big ball of mud, a monolith, and that keeps people up at night. They want to cut that down into smaller, more manageable pieces. So nothing really fancy happened in 1978, only that a couple of PHP developers who were recently at another conference decided 1978 was the best year ever, because reasons. All of those people were born in that year. I wasn't at the conference, but I still include that slide because reasons. 1983, another movie comes out. So War Games comes out. For me personally, that is one of the earliest movies that I remember watching, like actively watching and trying to understand what's going on, which is, I think, I don't know, to a large degree, it motivated me to get into this thing called computers, which was really fancy at the time. I didn't have one. It took like 7 more years until I got one, but that's how I started. And 1990, finally got my computer. On that machine, I learned programming in basic AREX, C, and assembly, mostly C and assembly, but that's besides the point. Around 2000, I was at the university, and that's when I, for the first time in my career, witnessed or experienced a hype. Suddenly, everyone was talking about service-oriented architecture. Like, we do not want the big monolith. We want to cut it down into smaller pieces that talk to each other using protocols. For instance, using SOAP. believe it or not, at some point in time, SOAP was meant to be an acronym. It was a simple object access protocol. In the second revision of that standard, they had this note: in previous versions of the specification, the SOAP name was an acronym. This is no longer the case. And they explicitly do not mention what words SOAP was an acronym for, because they realize it's not simple, and it's not very accessible. And so we hide that and just say, okay, this is SOAP, and everything is awesome if you use SOAP. Around 2012, microservices. People realized, yeah, these SOAP services, the protocol is not really nice. The services are still really, really big. So we are basically have big monoliths, smaller monoliths, but still monoliths that talk to each other. We need to cut that down even further, so we need microservices to make it smaller. So if you ask somebody what a microservice is, of course, like with everything else, you get different answers. But they usually fall into two categories. If you get an answer like, if you're looking for the textbook answer, then you get something like, yeah, a microservice, that's really easy. It's a mapper between an application protocol, something like REST, for instance, or SOAP, or whatever, and the domain model. And then you have the domain model, like your business rules, your business logic. And then underneath that, you have another layer of mappers where you map from the domain model to your persistence. So it's really easy. You have these three layers, the mapping between the domain model and the rest of the application using the application protocol, and the mapping between the domain model and persistence like the database, whatever. Of course, nobody built microservices like that. They didn't build them in the clean way. They basically built them the same way they would always build their software, so they turned out still too large, but now we had a term for it, and because the name has micro in it, everything is micro. So, however, that's not what happened. At least most pieces of software that I saw that were labeled or supposed to be microservices turned out to be a monolithic mapper from REST to SQL. Big, complicated pieces of code that do not really have any business logic in them, and that just are indistinguishable parts of, do I deal with REST here or do I deal with SQL here? And basically REST became the new SQL and everything was used interchangeably. Not really nice. But wait, there's more. You can do it even worse. You can build something like this. Yes, congratulations, you just replaced your big monolith that you had before with 20, 10, 100, whatever, microservices, and everybody talks to everybody, and nobody has an idea of what's going on where, and which protocol is used where, and what do I need to do when I want to deploy a change in one of those microservices, and how do I test microservice A in isolation from microservice B, and not really nice. So you exchanged your big monolith with a distributed monolith. That didn't give you any advantage, but now you have more disadvantages than you had before, because now you need to deal with asynchronous processing, you need to do with messaging and so on. Not fun. And then you see quotes like this, is where it's a truth universally acknowledged that a techie in possession of any production code whatsoever must be in want of a container platform, because the individual services of my distributed monolith, everything will be better if I put each and every one of those in a separate Docker container, because that will make the problem go away. Don't get me wrong, containers are really cool. They're a valuable tool that, if used right, can solve a lot of hard problems in an easy, convenient, efficient way. I've seen teams take their 15-year-old monolith with a couple of million lines of code, put that into a Docker container and call it a microservice. Because the way that they understood the domain that they were working in is, if it's in a Docker container, then it's a microservice by definition. And those things have nothing in common. One is an architectural pattern, the other is a technology tool. So, yeah, so containers will not fix your broken culture. They will also don't fix your distributed monolith. So around that time, when we, as a larger software engineering community, people who make their lives in building software, figured out, yeah, the idea of microservices is nice, but people are misunderstanding that. What usually happens in a situation like that is that you refine your definition of what that is, but it doesn't work to use that new definition with the existing name. You need a new name for that. And that's where we get to 2018. And of course, I need a movie reference, and that basically references the earlier movies. So we can skip that. The new term that came up last year was self-contained systems. Or, if you will, microservices done right. Or, if you will, software built right. But basically, any of these ideas that have to do with self-contained systems, none of them are new. Most of them have been around for decades. It's just that now finally people want to build software like that again. And it needs a new name because it has to be a new thing. So, what's the most important thing about the self-contained system? Each self-contained system is an autonomous web application. Each thing can do its job without having to rely on another of these things. So you do not end up with a distributed monolith. This means that you need to cut down your problem into small pieces, and that the small piece can be implemented in one piece of software that is accessible as an autonomous web application, as a self-contained system. And yes, that's hard. That requires thinking. That requires thinking upfront about architecture. Thinking is not going away, which I think is a good thing. Self-contained systems should not share business code with other self-contained systems, because that would just be a different manifestation of a dependency on a different system. Yeah, everything is better because service A no longer speaks via a protocol like REST to service B, but they both use the same code. Yeah, that doesn't really solve the problem. That may solve the runtime problems, but that doesn't solve problems with regard to scaling development teams. If team A works on service A and team B works on service B, and they need to collaborate on shared code, that doesn't give any benefits in improving velocity of the team. Infrastructure, such as database, for instance, should not be shared between self-contained systems. In the 80s and 90s, it was very, very popular to have an architecture or to build software using an architecture where at the core was the one integration database. Parts of the application did not use APIs or protocols or services or whatever to talk to each other. They used the database to talk to each other. The first time that I looked at a web service as a consultant, that was, I don't know, when was that? 2000, 2001, I went to my first customer. And the way that they implemented web services was, they had a MySQL database. In that MySQL database was a table with PHP code in it. And some people are already laughing and smiling. And yes, calling a web service meant fetch the PHP code from the MySQL database and then eval it. They had a really good explanation why they thought that this was a web service. In the end, at the end of the day, I figured out that they did this because they did not know that things like version control existed. So they used the database to distribute the code to all the servers, or make the code available on all the servers that they had. This is not a web service. And don't use the database to share information between different parts of the system. Always have well-defined APIs so you know who's talking to who and who uses what. Otherwise, you are lost when you try to figure out what code you can throw away when a feature is no longer needed. So, how do you test such a self-contained system then? Well, I'll give you an example. Can somebody guess what the example is going to be? Depends on whether or not you know the movie. There's a game missing. Tic-tac-toe is missing, so let's play tic-tac-toe. So let's say we have a service that we can contact via HTTP to play tic-tac-toe. This is a tool, by the way, that I did not mention in my tools talk this morning because it's not really related to PHP, but it's something that I started using a while ago whenever I need to interact for testing purposes or demo purposes with a web service. It's a tool called HTTP. HTTP like HTTP and pie like cake. And it gives you a command line tool named HTTP that allows you to make requests. It's basically a wrapper around curl, more convenient to use when you're working with and on web services. So what we're doing here is we make a GET request to that URL. And this is what we get. So we get some JSON back. There's an array representation. This is our board. Everything is empty because we have a new game. Then we can make a post request and say, OK, we occupy space number 5. If you didn't know, if you ever want to implement tic-tac-toe, and really only tic-tac-toe, not the generic NMK game, then the best representation for the board is an array of 9 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. Makes it later on really easy to detect the winning move. But that's outside the scope. So we basically say via this post request, I want to put my piece, or the current player wants to put his or her piece into the center of the grid. And when I make a GET request again, then I get the new state. Now I have an X in the middle. What I just did was a manual test. That's OK for a situation like that. I'm just working on that, trying to get some experience with that web service, trying to figure out whether it works the way that it was documented. But I did manual work. I don't know about you, I do not like manual work, at least when it comes to software development. Everything that can be automated should be automated. So it's manual. It's also end-to-end. End-to-end is a technical look at what the test does, meaning we use a real HTTP client to send a real HTTP request to a real HTTP server, triggering a real HTTP response that we evaluate using the client. End-to-end test has the advantage that it always works. The application I'm testing can be as badly implemented as you can imagine. I can always use it. I can always communicate with it end-to-end to test it. That always works. Otherwise, a real user using a real browser could not interact with it. That would be really bad. The disadvantage of end-to-end is that it's not really fine-grained. It's really useful information when an end-to-end test fails that some specific high-level thing currently does not work. But since everything is all the code is potentially executed, and there's communication with external systems probably involved, when a test fails, you do not know where the root cause for that is, and you have to potentially look at a lot of things to figure out the reason and to fix it then. It's also a system test because we look at the system as a whole. It's an acceptance test, meaning that I I'm looking at acceptance criteria. Maybe I have in some documentation, when I make a GET request, I get to see the current state of the board. And when I make a POST request like that, then that space is occupied, whatever. This is an acceptance test, like an outside perspective on the system. It's a functional test. And that word, unfortunately, has at least two meanings. Well, if you ask someone like me, it only has one meaning and everybody else is wrong. But I know that's rather harsh. But in computer science for a really long time, like 40, 50 years, functional test means any dynamic test that verifies functional correctness of a part of a software or of a software system as a whole. Dynamic testing meaning we're testing the software while executing the code. I have no idea how that happened, but when software testing came to web development, somebody used the name functional test for acceptance tests. So for instance, if you read the documentation for Symfony, they talk about functional tests and how functional tests are supported by their extension to PHP unit. What they basically do is end-to-end or edge-to-edge testing using PHP unit for acceptance testing, but they call it functional test, which is correct, but only to the degree that you're testing functional correctness, but also a unit test is a functional test because also a unit test tests functional correctness, but of a small part. Anyway, it's a dynamic test because we're executing the code, but we can do that in an automated way, using PHP unit, for instance, writing a tic-tac-toe test class that extends PHP unit framework test case, write a method test grid is originally empty, do an HTTP request to our endpoint, put that result, the string, into JSON decode, and assert using assert equals that we get some weird noises from the microphone. Or not, and that the grid is empty. Now we have an automated test. But the only thing we have changed is that it's no longer manual and now automated, so it's still an end-to-end test. We're still testing the whole thing from request to request. Still a system test because we look at the system. Still an acceptance test because we test an acceptance criteria. It's still a functional test because we still test functional correctness. It's still a dynamic test because we still execute the code. And if we execute the test, this is what it looks like. Rather boring. PHP unit, some version information, 1 dot to indicate progress while the tests are being executed, dot meaning successful test. Some statistics in the end, 1 test was executed, everything was fine. One of the most important questions when you're doing software testing is figure out what the smallest scope is in which you can perform the test. What is the least amount of code that you need to execute to test what you're interested in? The less code you execute during a test, the more precise the information will be when the test fails. When you have a unit test, and you test in that unit test a method, and that method has 5, 10, 15 lines of code, and the test fails. The reason for that test failure can only be in those 5, 10, 15 lines of code. And usually within a couple of seconds, you spot the mistake and can fix it and can move on. When you have a system-level test, an end-to-end test, and execute everything, the information that a certain feature or an aspect of a certain feature currently does not work is valuable and important, but it does not tell you where you should start looking for the root cause, because potentially it can be anywhere. Hopefully, you have both the small unit tests and the larger integration and end-to-end tests. So you never have a situation like the big test fails and no small test fails. That helps you pinpoint the location. But can we test this in a smaller scope? Can we test this while executing less code? And yes, we can do that. We need, or as a first step, we need to get rid of the HTTP communication. We need to get rid of the need to have a real HTTP client and a real HTTP server. So we do something like this. We instantiate our application object inside our test. We fake a GET request and let the application run with that faked GET request. And then look at the response and have the same assertion that we had before on the response object instead, or on response string rather, instead of having HTTP client make an HTTP request response to full circle and then look at that. That is a lot faster to execute because we don't have the network latency. Even if you run it locally, it takes some time. Runs in the same PHP process. Less code is executed. The web server is not involved. A lot less moving parts. Makes it easier to figure out what's going on when something fails. That is what is called an edge-to-edge test. It's the next smaller thing, smaller than an end-to-end test, since we are testing at the edges where the real HTTP request would start and where the real HTTP response would be sent out. Still an acceptance test, still a functional test, still a dynamic test. And again, can we test this in a smaller scope? Which brings us to actually specifying what we expect from our tic-tac-toe game, for instance. So maybe we should have started with that. Maybe we should have started by gathering requirements, business rules, domain logic, rules of our game, and describe, okay, game, the starting player is always X. And the current player, whoever is the current player, can occupy an empty space. And that, of course, implies that when the current player tries to occupy a space that is already occupied, that we get an error message and not that it's overwritten or something like that. When the current player has made a move, the next player, the second player, becomes the current player. The game hopefully can detect the winning move when the game is over. Hopefully it can also detect when there cannot be a winner, which is the more common case when you play tic-tac-toe. And we can list all of these rules and implement these rules in code. Yeah, for instance, with a unit test. Test starting player is X. We create a new game object. We retrieve the current player. And we assert that the current player for a fresh game is X. And we can go on. That is a unit test. That is a test that tests only a couple of lines of code in isolation from all of the dependencies. And when that test fails, we know exactly where to look for the root cause. We know exactly where to look and fix the problem. Yeah, and if you follow the best practice of giving your tests meaningful names, and test 1, test 2, test 3 are not meaningful names. Naming things is still one of the hardest problems in software engineering. You need to invest some time in good names so that tomorrow, next week, a year from now, you still understand what the code is about. And actually, these tests can help with that. If you have to test for something like this game, you can write down in the form of small, precise sentences and describe each aspect that you test with such a test. And then use these conventions, like if you have a test method that is named test starting player is X, is player X, PHP unit with this --test docs option can discard the test prefix of the method name and insert a space whenever there's a change in lowercase and uppercase in the camel case notation. Also works with snake case. And you get that output. And that output is really valuable. You can take an output, go to somebody on the project who is not a technical person, not a developer, and say, hey, this is how I understood your requirements. And this, by the way, is how the code, how the application currently works. This is automatically verified through tests. Did I understand what you meant correctly? And you do not have to look at code. You can look at this output. That's valuable for that. It's also very valuable when a new developer comes onto the team, needs to work for the very first time with this game object. He or she just runs the tests for that game object, looks at this output, knows the responsibilities and the environment of that, sees how that behaves in certain conditions. And when there is something specific that they're interested in, maybe, okay, can detect winning move. How do I do that? You just look at the code behind that test and see an executable example for how to use, how to reuse, how to interact with that piece of code that is tested there. And that's really powerful. You can think of these tests not only as executable documentation, but also as executable specification. So that's a unit test. Whole idea of these automated tests in general and the unit tests in particular was verification through execution. I execute a piece of code, for instance, a method, and verify that the thing that I expected to happen has happened. Usually there are, or commonly there are 3 things that you test about the method. You can test the return value. You can test that an exception is raised when an exception should be raised in error conditions. And the third thing, and sometimes sometimes really hard, side effects. And that side effect can be that the method call on one object leads to a method call on another object. That's where mock objects and spies come into play. Side effect could be that a statement is sent to the database that needs to be intercepted and then evaluated to see whether or not that happens, or you test it end-to-end, at least in that part, and look into the database afterwards and see whether or not the expected change happened in the database. That's verification through execution. And as I mentioned earlier, this is also executable documentation, but this is a realization that came much later. This is something that happened, I don't know, around 10 years ago, that we realized verification through execution is nice, but this is also documentation. And if I do test-driven development and write my tests first, it's actually executable specification. Step by step, I cut down the problem I'm tasked to solve into smaller, manageable pieces, and I document every step that I take in solving this problem in such a small test that along the way also documents how this thing that I'm currently working on actually works and is supposed to be used. This is really valuable. Yeah, the primary task of a developer is not the writing of code, but to understand the problem. The writing of tests helps to understand the problem step by step, what I just mentioned. And a common misunderstanding of test-driven development is that the tests drive the development as an end in itself. No, the tests trigger the required thinking to solve the problem and go to the next step. So, is this the end of the world as we know it and everybody fires their nukes and everything is over? Hopefully not. But I think there are some lessons to be learned or some things to think about. There it was again, the thinking. I promise that it's not going away. So software design is recursive. There are many things that you probably already know about at a smaller level, on the object level, for instance. Things like CQS, command query separation, getters and setters, or mutators and query methods. You do not mix, well, if you write clean code, then you do not mix reading and writing in the same method. Yeah, you do not violate the principle of least astonishment. Yeah, you have a method, that method has a name, and that method name describes what the method does. Yeah, if I have a method getX, then I expect that method to do nothing but return whatever X is supposed to be. I've seen plenty of times where if you look at version control, initially a method like getX started as a single line, return this X. 10 years later, it reads Y, changes X, talks to the database, calls a web service, does something completely different, and then returns X. That's a violation of the principle of least astonishment. As a user of that method that does not look into the body of that method when I want to use that, I'm pretty much astonished when I figure out, while searching for the root cause of a bug, that getX does something more than getX. Maybe there's a good reason why getX changed its behavior along the way, but when that happens, please rename that method to make it clear what happens. So on the object level, you do not mix these read and write operations. Software design is recursive, I said. But what does that mean? That means the same principle is applied not only on the object level, but also on the architecture level. There, it's called CQRS, Command Query Responsibility Segregation, which basically means that you treat the GET requests that come into your application completely different from requests that change state. Obviously also implying that GET requests do not mutate state somewhere on the server, in the database, whatever. So you want a clean separation there. Single responsibility principle can be applied, and that's where it comes from, on the object level. A class should be responsible for one thing and one thing only. There should only ever be one reason to change a class, because something in that class needs changing, not because I changed something in my front end and I changed some HTML, and now that class in my business logic needs to be changed. No, those things have nothing to do with each other. Or I changed something in the database, and now no. Single responsibility principle. There should only ever be one reason to change that thing. And you can also apply that on the architectural level, which brings us back to the microservices, which should now be called self-contained systems. Such a service should be responsible for one thing. And if it's only responsible for one thing, then it doesn't need to talk to somebody else to get its job done. Then you can compose bigger things from these self-contained systems. And then suddenly it gets really easy to test them in isolation from each other, to deploy them on different roadmaps and at different points in time. And everything is a lot easier and more awesome. And hopefully, people will really start to implement software like that. Yeah, and in closing the loop, think not only talking about implementation, but also understanding the problem domain and making it manageable, cutting it down. That's what domain-driven design means by bounded contexts. And in such a, whatever you want to call it microservice, call it a well-written microservice, or call it a self-contained system, there should be only functionality related to one bounded context in there. Because then, almost by definition, you get to a place where you do not have the dependencies and run into a nightmare. Okay. That brings me to the end. I hope that was interesting. I shared with you the secret in the beginning that I didn't really know what I was going into, and that it might involve some time travel and looking back at how we did things in the past and how that slowly evolved over time. And I hope that this was, at least to some degree, useful to you. Thank you.